Hi team, we're ready for section 9.3, systems of nonlinear equations and inequalities. We're going to be dealing with just two variables. Remember, if we have two variables, then we need two equations or inequalities. A system of nonlinear equations is a system where you have at least two equations with at least two variables, but at least one of those equations is not linear. So even though it says a system of nonlinear, one of them could be linear, but they can't both be linear. And we're going to use the methods that we've used before, elimination, also called the addition method, and substitution methods. So let's take a look at example 1. When we're solving linear equations, it's nice to generally label our equations so we know which one we're working with at which time. Since in A, we have squared variables and single variables to the first exponent, linear variables, then it's probably best if we use substitution. It's up to us whether or not we want to solve for X or Y, but I would probably solve for the Y value in equation B because it has an exponent of 1 and only a -1 coefficient. So let's get that Y by itself. We're going to subtract 3x from both sides, so that would give us a -3x plus 10. Divide everybody by that -1, and we get y equals a positive 3x minus 10. So now we have a value for y with x. We were going to substitute into equation A. So remember, equation A is x squared plus y squared equals 100. So we're going to take that binomial that represents y, and we're going to plug it in here for y. So we get x squared plus 3x minus 10 squared equals 100. Go ahead and FOIL and combine like terms. And since we ended up with a quadratic, let's set it equal to 0 and see if we can factor. And this gives us two possible solutions for x. Either the first factor equals 0, which means x would equal 0, or the second factor equals 0, which means x would be 6. So remember, to solve any system of equations, we're looking for points or lines that satisfy both. So if x equals 0 and x equals 6, let's find what their corresponding y's will be. So let's first focus on the fact that x equals 0. We are going to use equation B, which is 3x minus y equals 10. So if we substitute in that x equals 0, we would get 3 times 0 minus y equals 10, which would give us a y of -10. So we get the point 0, -10. Now let's plug in our second x value of x equals 6 into our equation B of 3x minus y equals 10. We could have plugged it into A. It's just B would be easier since it's already linear. So we get 3 times 6 minus y equals 10. 18 minus y equals 10. So that means y equals 8. So we get the point 6, 8. So those are our two solutions, 0, -10, and 6, 8. Now let's take a look at problem B. Again, we have equation A and equation B. The nice thing is both equations have x squareds and y squared, so we can use the elimination method. We can keep A as is and multiply equation B by a -1. So when we add the two equations, we're left with a 3x squared equals 3. Divide by 3, we get x squared equals 1. So we get two possible values for x. We take the square root, we get x equals either a -1 or x equals 1. So let's look at both possible solutions. If we first look at x equals -1, again, we can use equation A or B. It just B seems a little bit more simplified. There's no coefficients. So I would prefer to use B, x squared plus y squared equals 10. So if you plug in a -1 for the x squared, 1 plus y squared equals 10. So y squared equals 9, which again, when we take the square root, we have to consider both the positive and negative square root of 9, which would be plus or minus 3. So this gives us two possible points. We have -1, positive 3, and -1, negative 3. Now we have to do the same thing with the second value of x, which is a positive 1. And you may have already guessed, since we're squaring that x value, whether it was a 1 or a -1, we're going to get the exact same y values. So we know y squared is going to be a 9, so y is going to be a plus or minus 3. So that gives us a +1, positive 3, and a +1, negative 3. So in this case, we ended up with 4 points where these two graphs intersect. Now, depending on the type of equations we have, which gives us particular types of graphs, will dictate how many solutions we might have. For example, in that first block, we have a parabola and a line. We may have no solutions because they don't share any points. One solution, they may just intersect at one point, or two solutions. The same can happen if it was a circle and a line. But as we scroll down, what if we had two circles? They might not intersect at all. They may intersect at only 1. They could intersect at 2, 3, or possibly 4, unless they were the exact same circle and they were right on top of each other and they intersect in all possible points. Now let's take a look at a system of inequalities. Again, it's a system of at least 2 inequalities with at least 2 variables, but not all of those inequalities are linear. The unique thing about inequalities is the solutions are typically regions. The solution to a nonlinear system of inequalities is the shaded region in common. In other words, it's where any shaded solution regions overlap, or where the regions intersect. This is called the feasible region. So let's remind ourselves just how to do a graph of a single inequality. So let's say we have x squared plus y squared is less than 25. You may or may not recognize that as a circle. You remember x value minus the h squared plus the y value minus the k value squared equals r squared is a circle. So in this case, our center, the hk, is going to be 0, 0, and our radius is going to be 5. So if we were to graph that equation, notice we have an inequality here, but also particularly that inequality is a strictly less than, there's no equals to. So for those guys, we want to use dotted lines. Okay, and for some of you, if you're doing it by hand and you're wanting to show me something, I've had students on tests before kind of write the word dotted because they'd forgotten and then they erased it, you know, so they didn't have to do everything. That's fine, as long as I can tell that it's dotted. But on the left-hand side, that represents the circle. The right-hand side is just the radius. So it's saying that the circle, the shaded area should be smaller than a radius of 5. This is the smaller, that's where the 5, here's where our solution is. So where is the circle smaller than a radius of 5? It's on the inside. So one thing that helps when you're graphing inequalities is to see how many regions does that graph split the space into. Well, the circle has 2 spaces. It has the space outside of the circle and the space inside of the circle. So only one of those is going to be shaded. Since it's smaller, we would shade the inside of the circle. So now let's focus on what's involved when we're graphing a system of nonlinear inequalities. When we're doing this by hand, we first want to find the intersection points. And we do that by solving the corresponding system But we do it in terms of just equations, just like we did on that first page. We set them up as equations. Where will they meet? So we at least know to have those points involved. Then we want to graph the equations. And remember, when we're given strictly less than or strictly greater than, we're going to use dotted curves. If we are given less than or equal to or greater than or equal to, we are going to use solid curves. And we shade the side of the curves that satisfies that inequality, but we do each one separately first. In other words, where's the first one satisfied? Shade that. Where's the second one satisfied? Shade that. So there's a couple of ways to look. The first one, if we are able to solve for y, in other words, to get y by itself, we didn't with the circle, but if it was a line or a quadratic or somehow that we can solve, you shade the region that satisfies that y side of the inequality. In other words, if you have a y is larger, you shade above the graph. If y is larger, y's get larger as you go up. So you shade above wherever the graph is. Just pick a point, go up. That's where you shade. If y is less than, in other words, smaller, you shade below the graph because y's get smaller as you go down. So pick any point on the graph, go down, that's the area where we shade. Otherwise, we can pick test points on either side of the curve to determine which side will satisfy the inequality. Plug in this xy value. Does it work? Is it less than or greater than, whatever we're looking for? If not, go to the other side. Look for all the regions that that graph creates. Last but not least, we want to identify the feasible region. So if we do it graphically, we're going to do it by illustrating the intersection or the overlapping area of the shaded region. So that's why you want to lightly shade the area that satisfies, because the overlapping area should be shaded a little bit darker. If we do it algebraically, then we want to see where do they intersect, which points do they intersect, and which area satisfies both. So let's do example 3. They want us to graph each system of nonlinear inequalities, clearly shade the feasible solution region with its intersection points. So let's find the intersection points. We're going to work this with equation A and equation B. So let's leave A as it is, but change it to an equation equals to. I want to eliminate the y values. So I'm going to multiply equation B by -1. So I get a -2x plus y equals a +1. So when we combine these, we get the equation x squared minus 2x equals 3. And since it is a quadratic, let's set it equal to 0, see if we can factor. And we get an x minus 3 and an x plus 1 equals 0. So that gives us 2 possible x values. X equals 3 and x equals -1. But again, we have to find those corresponding y values. So let's first start with x equals 3. Equation B just happens to seem simpler. So if we plug in 3 for our x, we get 6 minus y equals -1. So -y equals -7, or y equals 7. So this guy gives us the point 37. Then we have to try our second x value, which is x equals -1. Again, we're going to plug it into our B equation. So we get 2 times -1 minus y equals -1. -2 minus y equals -1. So -y equals 1, so y also equals -1. So we get the point -1, -1. So we have 2 intersection points at -1, -1, and 3, 7. So let's graph it and determine whether or not it lies between those 2 points above where that region is represented. So equation A is a quadratic. So if we solve for the y value, -2 less than or equal to y, that means we have a quadratic equation that's been shifted down 2 units. So here's at -2. But I also know that they intersect at -1, -1, so that's a value on it, and at 3, 7. So I know that those points are on my quadratic as well. Got the vertex, and remember it's symmetrical. So I know if I'm at -1, over here I'm going to be at 1. If I'm at 7 at 3, I'm also going to be 7 at -3. And it has the less than or equals to, so that tells me I'm going to draw the solid parabola there for equation A. Now I need to know where to shade. Are my solutions above this graph going up, or is it below? Well, I'm going to focus here. My y is on the larger side of that inequality, so I want my y to be larger. So I can take any point, and let's say I pick this point, I want my y to be larger, so that means I'm going up. At any point on here, I'm going to go up where my y's are larger. So for this inequality, my shading is going to be above the graph. It looks like it's inside the parabola. But again, you can always use a test point to see where that would land. Now let's do equation B. If I solve for my y, we would get 2x plus 1 is greater than y. I'm not dividing by, I'm just adding and subtracting, so none of my inequalities changed. Here we have a linear equation. But remember, we already know that these 2 points are in common, so we could just draw the line. We know it's at -1, 1, and up here at 3, 7, but it has a strictly greater than, so the line is going to be dotted. So now we have to determine where are we going to shade this graph. Well, notice y is on the smaller side of the graph. So if we look at this graph, if y is smaller, I pick a point on the line, and that means I'm going to choose where the y's are smaller, which is downwards. So for this guy, we would shade below the graph. So the question is, what region, remember we have to use those little points, what region does it satisfy both? Well, the region where they overlap is here. So that's the region that satisfies. Now I wanted to take a look at some of the homework here because I know some people struggle with how to graph these. So this is question 8 from your homework. The top one is a parabola. I want you to find the points of intersection. I'm only going to show you how to graph it using the tool in MOM. But this top one is going to have a solid curve. So I'm going to choose parabola with the solid. And then I'm going to pick 2 points that are on that graph. Well, I know there's a point at -2, and I know there's a point at 2, 4. So I'm going to graph it right there. But then I have to determine where to shade it. The y is larger than this graph, so I'm going to shade it in here. In order to choose where to shade it, you hover over the area until it's shaded and then click on a point. Just click on it, and that tells it shade that one there. Now let's graph the second one. Notice this guy is linear, but it's strictly greater than, so I'm going to use the dotted line version down here. It has a y-intercept of -1, so I'm going to choose that as a point. And then it's a slope of -1, so I can go down 1, right 1 if I want, or up 1, left 1, however I want to do it, and I'm going to make that a point. But the y is larger for that one as well, so I'm going to choose to shade upwards. On these, that's all you do. They don't ask you where the common region is. They just assume, okay, you've shaded them both correctly. Surely you can see where they overlap. Submit the question, and hey, I didn't do something right. I wonder what they didn't like. Maybe it was my parabola. But you get the idea. So apparently I didn't even do one of those correctly. So anyway, so if you have any questions, please don't hesitate to ask me or come by and see me. Thanks. Bye.